take a look back at the early stages of the universe, and the James Webb Space Telescope has been doing exactly that. It has captured 6 galaxies on camera that are among the earliest examples we've seen. However, they're a little faded at the moment. This moment takes us back to the very beginnings of the universe. The message from the James Webb Space Telescope, pertaining to what lies at the edge of the observable universe, has sparked unprecedented curiosity and excitement. When the JWST was first launched, its goal was evident: to look into deep space beyond any previous scope, unraveling the mysteries of the universe's origin, structure, and perhaps even its ultimate fate. This momentous occasion, when the telescope revealed its findings about the outermost reaches of the universe, marked a pivotal moment in our understanding of the cosmos. For centuries, humanity has wondered about what lies beyond the stars, and now we have received the most in-depth glimpse of the far-off frontier of space. Before proceeding with the details, don't forget to hit the like and subscribe buttons for more exclusive news. The observable universe is an astonishingly vast region, stretching approximately 93 billion light-years in diameter. This measurement represents the universe visible to us on Earth, limited by the speed of light and the age of the universe. As we look further into space, we are essentially gazing back in time because the light we see from faraway objects has taken billions of years to reach us. The James Webb Space Telescope was built to study these distant objects by operating in infrared wavelengths, which can pass through cosmic dust and reveal ancient galaxies and stars. When the announcement came that the JWST had successfully gathered information from the farthest reaches of the observable universe, it was a moment of profound significance. Near the boundary of the observable universe, the JWST discovered galaxies that existed when the universe was only a few hundred million years old. These galaxies are faint and distant. However, their light has traveled billions of years before reaching us. This represents a glimpse into the early years of the universe, enabling scientists to examine the formation of the first galaxies. The results indicate that, even in the earliest epochs of the universe's history, galaxies were growing at a faster rate and in higher numbers than previously thought. This challenges existing models of galaxy formation and demonstrates that the early universe was considerably more dynamic than anyone had imagined. One of the most fascinating aspects of these discoveries is redshift, which refers to the extent to which an object's light has been stretched as it travels through space. The greater the redshift, the farther away and older the object is. The JWST's ability to detect galaxies with extremely high redshifts indicates that we can now observe light emitted shortly after the Big Bang. These galaxies, located near the edge of the observable universe, provide essential data about the early stages of cosmic evolution. As we study these ancient structures, we gain insight into how matter began to coalesce into stars, eventually leading to the creation of galaxies and the vast, multifaceted universe we inhabit today. The implications of these discoveries are profound. By observing the edge of the observable universe, we are, in essence, witnessing the universe's infancy. This period, known as the cosmic dawn, has long eluded detailed study due to the limitations of previous telescopes. However, the James Webb Space Telescope, with its advanced capabilities, is now able to shed light, both literally and figuratively, on this enigmatic era in cosmic history. The galaxies detected at the boundaries of the observable universe are not just relics of the past. They are also key to understanding the processes that led to the development of larger structures such as galaxy clusters, superclusters, and, ultimately, the large-scale structure of the universe itself. In addition to offering fresh perspectives on galaxy formation, the JWST's findings raise questions about the nature of dark matter and dark energy. These two mysterious components make up the majority of the universe, yet they remain poorly understood. The data gathered from the farthest reaches of the observable universe may provide clues about how dark matter influenced the initial development of galaxies and how dark energy has driven the universe's expansion. When the universe was merely 100 million years old, a tiny fraction of its current age of 13.8 billion years, it was just beginning to form primordial galaxies. The redshifted light from these dim, ancient galaxies, stretched by the universe's expansion, offers a unique window into the earliest stages of cosmic development. Before the James Webb Space Telescope, astronomers relied heavily on the Hubble Space Telescope, which provided groundbreaking insights into the universe. However, Hubble's capabilities were limited when it came to observing the very first galaxies and stars. The JWST's ability to detect infrared light, which has been stretched by the universe's expansion, has allowed scientists to look further into the past than ever before. By capturing images and data from a time when the universe was less than 1 billion years old, the JWST has revealed that the early universe was more than just a few tiny specks of light. It was a dynamic period of formation. The first galaxies, and perhaps even the very first stars, known as population 3 stars, were forming. These stars, made entirely of hydrogen and helium, are believed to have burned through their nuclear fuel quickly before exploding in supernovae, seeding the cosmos with heavier elements essential for the formation of planets, life, and everything we know today. The discovery of these ancient galaxies and stars is crucial for understanding the processes that led to the creation of the complex universe we see now. Additionally, it raises significant questions about the structure and boundaries of the universe. When we discuss the end of the observable universe, it is important to clarify that this is not a physical boundary. Instead, it represents the farthest point we can see, limited by the finite speed of light and the expansion of the universe. Beyond this horizon, the universe likely continues, but we have no way of observing it because its light has not yet reached us. The JWST's ability to push the limits of our observable universe opens new doors and possibilities for understanding what lies beyond that horizon. One of the most tantalizing implications of its discoveries is the insight they provide into the universe's expansion. Since the Big Bang, the universe has been expanding, and this expansion appears to be accelerating due to a mysterious force known as dark energy. By studying galaxies at the edge of the observable universe, the JWST helps astronomers measure the rate of expansion more precisely. Understanding the nature and behavior of dark energy could fundamentally reshape our theories about the universe's future and ultimate fate. The universe. Galaxies will continue to expand forever, drifting apart more and more until the space-burning stars become either a cold, dark void or something else, depending on how dark energy changes over time. This change may be responsible for the universe regaining its internal collapse, leading to what is known as the Big Crunch. Questions regarding this will be assisted by JWST data, which will help answer key queries. Findings at the edge of the observable universe force us to reconsider our comprehension of cosmology, particularly the concept of rapid inflation. The momentary expansion of the universe following the Big Bang, also known as inflation, implies that the universe grew exponentially in the first fractions of a second, smoothing out any irregularities and establishing the conditions for large-scale galaxy formation. However, if the JWST discovers anomalies or unforeseen structures in these distant galaxies, it could challenge the inflationary model, encouraging physicists to refine or even completely rethink our current understanding of the universe's early moments. Beyond the implications for cosmology, these discoveries hold philosophical and existential significance. The discovery of the most distant galaxies prompts fundamental questions about our place in the universe. What lies beyond the observable universe? Does a multiverse exist, with countless other universes, each with its own set of physical laws and conditions? Some theories suggest that the observable universe is just one bubble in a vast multiverse, where other bubbles exist outside our cosmos. If this were true, it would imply that the universe we see is only a tiny part of a much more expansive and intricate reality. These discoveries also highlight the scope and limits of human knowledge. As we look deeper into space, we realize how small and fragile our planet is in the grandest scheme of things. Yet, at the same time, our ability to observe and comprehend the universe at this level is a testament to human ingenuity and curiosity. The James Webb Space Telescope symbolizes the pinnacle of decades of scientific and engineering effort. The discoveries it makes will shape our understanding of the universe for generations to come. In addition to expanding our knowledge of the universe's origins, JWST observations at the edge of the observable universe will likely have practical implications for the search for life on other planets. By studying the first stars and galaxies, astronomers can learn more about the conditions required for life, such as the presence of essential elements like oxygen and carbon. This, in turn, enhances our understanding of where life might exist elsewhere in the universe. While stars and galaxies at the edge of the observable universe are too far away to directly identify life signs, Studying their formation can help us estimate how frequently planets with life might exist. This announcement also underscores the importance of collaboration and international cooperation in advancing our understanding of the universe. The JWST is a joint project of NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA. Its accomplishments are a testament to the power of global collaboration. No single nation or company could have built and operated such an intricate and advanced telescope alone. The telescope's discoveries, including its observations at the edge of the observable universe, are the result of the combined efforts of thousands of scientists, engineers, and technicians from all over the world. James Webb's discoveries do more than merely extend the boundaries of what we can see. They fundamentally challenge some of the most widely held beliefs in cosmology, astrophysics, and even philosophy. To grasp the full significance of these findings, we must explore the intricate and often bewildering details of how the observable universe functions. One of the most significant implications of JWST's findings is their potential to refine or redefine the standard model of cosmology. The standard model describes the universe's expansion from the Big Bang, around 13.8 billion years ago, to the present. Embedded within this model are assumptions about how matter and energy behave on vast scales, the early universe's rapid inflation, and the mysterious nature of dark matter and dark energy. However, discoveries at the edge of the observable universe could challenge these assumptions. The earliest galaxies and stars captured by JWST appear to be unlike anything we observe in the local universe. They seem more massive, and their formation times may be much earlier than previously expected. These findings could indicate that our current models of galaxy formation, based on the cooling of gas and the clustering of dark matter halos, need revision. If JWST is observing galaxies older than our models predict, cosmologists may have to rethink the processes that drove the early formation of galaxies. There are also more speculative theories that these discoveries could impact. For instance, some researchers propose that the entire universe is a hologram. The holographic principle suggests that all the information describing our universe could be encoded in 2 dimensions on a distant surface, much like how a hologram encodes a 3-dimensional image on a 2-dimensional surface. This idea arises from efforts to reconcile quantum mechanics and general relativity, particularly in the study of black holes. While this theory remains highly theoretical, discoveries that extend our understanding of the farthest regions of the universe may provide new insights into these fundamental questions. Perhaps what we think of as the edge of the observable universe is not an actual boundary, but rather a region where different physical laws or ways of perceiving space and time come into play. JWST's revelations about the contents of the observable universe intersect with key debates in general relativity as well. In Einstein's theory of relativity, space and time are intimately connected, forming a 4-dimensional fabric known as spacetime. The telescope's ability to see so far back in the universe's history means we are also looking into the past, at a time when conditions were radically different from today. One of the most fascinating aspects of JWST's discoveries is how they refine our understanding of the early universe's timeline. The beginning of the universe was filled with a dense, hot plasma, where atoms had not yet formed. As the universe expanded and cooled, it reached a phase called recombination, when electrons and protons combined to form neutral hydrogen, allowing light to travel freely for the first time. This event produced the cosmic microwave background, CMB, the oldest light we can observe. However, the galaxy's JWST has observed date to a period shortly after this era, when the first stars began to ionize the surrounding hydrogen, shaping the universe as we know it.